Modern data can be massive and messy. Modern, massive, messy data is often called big data. And our first goal is to understand exactly what we mean by this term, big data. So what is data science? Let's ask an expert. ChatGPT.
Data science is an interdisciplinary field that involves the extraction of knowledge and insights from data. It combines various techniques, tools, and methods from statistics, computer science, and domain knowledge to analyze and interpret large and complex datasets. The primary goal of data science is to extract meaningful information and actionable insights from raw data, enabling data-driven decision-making and solving real-world problems. Key components of data science include data collection, the process of gathering relevant and diverse datasets from various sources, including databases, APIs, web scraping, sensors.
So this is a long response, but it is not a fancy Google search. It's instead what's known as a large language model. And a large language model generates a unique response from a variety of sources that it has, quote, Googled. For example, what is data science, but this time in the style of Hemingway?
Data science, a modern alchemy. From the depths of ones and zeros emerges meaning, like fish rising from the murky waters. The art of numbers, a dance of statistics and machines, woven with the threads of human wisdom. Raw data, a rugged landscape, is tamed and molded, revealing its secrets through careful observation and experimentation. The models, like characters in a story, come alive, predicting the future and unraveling the past. In this digital age, the scientist wields the quill of code, crafting narratives of insight, etching graphs and charts that tell tales of patterns and truths. And thus, from the tangled web of data, emerges knowledge, a beacon in the fog of uncertainty.
So as you can imagine, a large language model requires huge amounts of big data. And also, this Jarvis-style vocalization of the responses, it also required huge amounts of big audio data in order for the algorithm to learn to make this natural-sounding human voice. Data science is the study of such big data. So what is big data? It refers to data sets that are both large as well as complex. Complexity is the mathematical term for high variety. Complexity means the data has a complicated underlying structure. A document, for instance, is a word structure. It's not just a set of words. Curves are point structures. They're not just sets of points. So very often a curve has an orientation. So for instance, the real number line has an orientation from left to right. That's a structure, not just a set. That is, structure is as important as size. So the big data has often been characterized using what's known as the 3 V's by Gartner, saying that big data has high volume, has high velocity, and has high variety. And those 3 mean that we have to come up with new ways of looking at the data. We also want data to be high veracity, reliable, high quality, low noise, unbiased, and so on and so forth. So high veracity means that even big data can be bad data. Let's look at an example. Let's factor x to the 4th plus 4. Well, it's not so hard. We insert a 4x squared and subtract a 4x squared. The first one is a perfect square minus the second, 2x squared. Difference of 2 squares, and we have a first step factorization of x to the 4th plus 4.
The expression x caret 4 plus 4 can be factored using both real and complex numbers. The factorization is as follows: x caret 4 plus 4 equals x squared plus 2, x caret 2 to 2. This is a difference of squares pattern. where we have used the formula a squared b squared equals a plus b, a, b, with a equals x squared and b equals 2. So, the expression x caret 4 plus 4 can be factored as x squared plus 2, x caret 2 to 2.
However, this would imply that x to the fourth plus 4 is the same as x to the fourth minus 4. It's just wrong. And it's a common high school mistake. And ChatGPT was originally trained, and the one we're using was trained from an internet rampant with these high school style mistakes. So high veracity is non-trivial, but it's also an issue more appropriate to a different course, for example, one in experimental design. And that's where we're going to leave the in-depth study of high veracity. So with the 3 V's, we have high volume, high velocity, and high variety. For example, large language models require huge collections of documents, websites, Wikipedia, novels. But you could not build a large language model solely from dictionaries. Dictionaries do not inform an LLM on how to form sentences and paragraphs. A dictionary is a set of words. Of course, there's definitions for those words, but there's no usages of those words. And in a document, the information is due both to the structure and the words. Even seemingly ordinary data. So data that you may have already encountered, rectangular arrays. It can occur in a surprisingly high variety of ways. So a rectangular array is m observations of n features, where the rows are the observations, the columns are the features. It's m by n array. And the set of all possible m by n arrays is denoted this blackboard bold superscript m times n. M is often very large, which is often where we get the high volume from. But let's explore the high variety of ways in which rectangular arrays occur as big data. For example, movie streaming. Viewers rate movies that they stream. The ratings are often, say, 1 to 5. And if you don't rate a movie, haven't seen it, for instance, then that's usually recorded by a 0. Here's an example of that kind of rectangular array. Notice that each viewer only rates a small percentage of all the movies that are available. There's tens of thousands of movies, but how many movies have you watched? Maybe 100, 200. So most of the ratings are zeros. In other words, most of the movies are not rated by a given viewer. An array in which most of the coefficients are 0 is said to be sparse. Here's another example of a rectangular array. So we have across the top the features are the plays of Shakespeare, and then all the words that occur in all of the different plays form the rows. For example, 73 implies that Antony occurs 73 times in Julius Caesar. It's a sparse matrix. Only a small percentage of the coefficients are actually non-zero. Grayscale images, you have a rectangle of pixel intensities ranging from 0 black to 1 white. So you can see the black areas are 0, but most of the image isn't black. So this is what's known as a dense matrix. Most of the coefficients are not 0. Graphs or networks, you have vertices connected by edges. And to study those, we often use what's called an incidence matrix. Each row corresponds to an edge. The columns are the vertices. And if an edge starts at A and ends at C, then you have a -1 where it starts and a +1 where it ends. And everything else is zeros. If I add an edge, then it adds a row, but only 2 non-zero coefficients. Everything else is zeros. So this again is for a big network, this would be mostly zeros. In other words, it's sparse. But time series, the sequences of values in time, not sparse. So rectangles will play a major role in this course, and that means we're going to use matrix algebra. Now we'll review and introduce concepts in linear algebra as needed, but I assume you know the following at this point: dot products, matrix multiplication, and properties of dot products, or in particular real inner products. This u dot v is the norm u norm v, Euclidean norms, cosine theta. That actually is a very important concept in data science. And we'll have a review session, and I'll go into more detail then. And also we use sigma notation. For instance, our dot product will be written as a sum. And you see here, I may not always indicate exactly what the starting index and what the ending index is. The summation notation is for communication, for us to understand what's going on. So rectangles, boxes, and boxes of rectangles. You see, we could have rectangles making up data sets. A box of rectangles, which is often called a tensor, or a collection of spreadsheets, if you want to think of it that way. And it's often this compound tensorial structure that gives us the large size. For example, if you have 100 spreadsheets with 100 observations of 100 factors, that's 1,000,000 data points. For example, movie streaming. So viewers download and stream, watch movies, and then give them ratings. But they do that every single day. So we actually have a rectangle of movie streaming ratings for every single day. So if you've got millions of viewers times thousands of movies times thousands of days, you're looking at trillions of data points. In other words, high volume often comes from the huge number of observations of high variety data structures with many variables. Now, big data is modern data, but modern data is not always big. And so one of the things we'll see in this class is we often will not use massive data sets, but just medium-sized data, as long as we're developing the skills and models necessary for high variety data. Now, sometimes high variety unavoidably implies high volume and high velocity, but to the extent possible, we'll try to focus on high variety. And what does that mean? High variety means that big data has a complex shape. Data arrive in either unstructured or structured formats, may have to be transformed before we can do anything with it. And data science is what we do with big data, typically with algorithms known as predictive models. So a predictive model assigns a probability to every possible observation or sample of the features. Now this is probably a very new idea to you, so take this as just a simple first introduction to this concept. We'll be exploring predictive models every week for this entire semester. But the result is you get a probability distribution on a feature space of possible observations with the structures of those observations. For example, toss a fair coin and then toss it again. Here are the set of all possible observations. We might see tails then tails, or tails then heads, or heads then tails, or heads then heads. Notice because of the structure, we have a first coin toss then a second, even though we have the same set of outcomes for possibilities 2 and 3, we have different structures. So tails then heads is different than heads then tails. So here is our assignment of probability to each of these possible observations with the structure of one following the other. A generative model, which will be very important to us, samples a predictive model, sampling a probability distribution for whatever is most likely. It's usually conditional, so given a query, sample for a high probability possible structured observation For example, suppose we had a massive data set of 4-word phrases that occur in textbooks and articles on elocution. A predictive model would say, assign a probability for the last 2 words conditioned upon or given the first 2 words. And then a query like how now with high likelihood would generate the completion brown cow. So generative models produce structured data. LLMs can also learn computer languages, for example. Computer language is a few words, but lots of structure. Let's look at an example. Let's ask ChatGPT, how would I produce a scatter plot with trendline in Python using a data frame? Well, I've got the voice turned off, but you can see you import the necessary libraries. You create or load your data frame. You have the trend line computation, and then the plot. So all of this was generated by ChatGPT. So here is the ChatGPT Python output. Here it is in what's known as a Jupyter notebook that you can execute, and executing that gives you your desired result. In fact, one of the most important applications of large language models is as code-generating tools and tutors or assistants for new programmers. In fact, you don't know Python, a lot of what you're going to learn about Python over the next few weeks is almost certainly going to be taught to you by these assistants. Let's look at an example. This is Anaconda Cloud. And notice that I entered create a data frame and then plot with trendline in Python. And you can see here in Anaconda Cloud, it's generating the code. There is the code. I clicked run it in the notebook and it didn't work. So ChatGPTs and large language models in general are not perfect. It forgot to tell me to import NumPy. But then once I import NumPy as NP, then I'm fine. I could have actually interacted with the assistant, and the two of us together could have debugged and tried to figure out what was going wrong here. But I'll let you play with that. So data science is the study of big data. Predictive models extract an often massive amount of structured information from often messy data by assigning probabilities to possible observations, which conversely can be sampled to generate new information. So an important part of data science is methods and models for extracting information from big data. Predictive models can also be combined with other types of models, such as what are known as physics-informed learning. Most importantly, ChatGPT shows us data science is driven by 3V satisfying large, complex, big data sets. Big data is large and complex, high velocity, high variety, and high volume. And often the three together allows us to use the complex underlying structure to generate responses or make predictions, as we saw with ChatGPT.